Hello, everyone. Today we are going to talk about dynamic programming. Dynamic programming is a very powerful technique for designing algorithms. And this technique is going to work with problems in which we can uh, split the original problem into smaller ones, as long as those decomposed or broken sub-problems overlap between them, among them. Um, Most of the problems that can be solved in this way can also be solved by using, let's say, traditional plain recursion or recursive solutions. However, those solutions are usually very inefficient because we will be solving the same problem over and over again. So the question is, how can I what can I do in order to preserve this idea of decomposing the problems, but instead of repeating work, take advantage to the fact that some of those sub-problems are similar, and then use that in order to make a more efficient solution. And the way we will do it is by saving or storing those solutions so that we can just make use of them if we need them. All right? This technique was invented by the American mathematician Richard Bellman in the 50s because he was solving some optimization problems. And it was later taken by the computer science community. That is why in this context, the word programming doesn't actually mean writing code on the computer, but to use a table in order to store and retrieve information, or what is also called in other areas a tabular method. The main idea of dynamic programming is that we set up a recurrence relation or a recursive solution that decomposes the original, usually large instances, into some smaller ones. Then we solve those smaller instances once. We record the solution in a table, and then by doing so, we can extract the solution to the initial big instance of the problem from that table. And in order to illustrate this process and this technique, the idea of this technique, we will go back again to this problem that I am sure you are very familiar with, the computation of the Fibonacci numbers. We may remember that the definition, the simple definition of the Fibonacci function is going to be a recursive one. And in this case, we basically say that if we want to compute the Fibonacci of n, then we will add the Fibonacci of n minus 1 and Fibonacci of n minus 2 for any value n bigger than 1. And this is a recurrence because we can see, of course, that in order to compute the Fibonacci of the number, we need the Fibonacci of two other numbers. So, and we are given with initial conditions, f of 0, the Fibonacci of 0 is going to be 0, and the Fibonacci of 1 is going to be 1. In some other books, they start the conditions by saying the Fibonacci of 1 is 1, the Fibonacci of 2 is 1, 2, and then we can perform the recurrence in order to solve the problem. Either way, we have this definition. And if we want to implement directly the recurrence in a computer program, The thing is that we will have a very inefficient program because it will have to recompute the same values many times. And in order to see that, um, let's suppose that we have, let me insert a blank page here, and then we can, for instance, consider the problem of computing the Fibonacci of 4. In order to do that, I will need to compute the Fibonacci of 3 and the Fibonacci of 2, according to the formula. Remember, the formula said Fibonacci of n is going to be Fibonacci of n minus 1 plus Fibonacci of n minus 2. So to compute the Fibonacci of 3, then I will need to compute the Fibonacci of 2 and the Fibonacci of 1. In order to compute the Fibonacci of 2 here, I will need the Fibonacci of 1 plus the Fibonacci of 0. Here, I will need the Fibonacci of 1 and the Fibonacci of 0. Here, oh, this is one of the initial conditions. So let me use a different color. Here. So here, this is a this is a initial condition. So this is going to be, I'm sorry, this is going to be 0. This is going to be 1. This is going to be 1. This is going to be 1. This is going to be 0. And with those numbers, I can start, or the recursion can start going back in order to perform all the computations backwards. But the thing that I want to point out right now is the following. Let's take a look at this box here. Is the same as here, you see? And then this one here is the same as this one here, and is the same of this one here. And this one over here, Fibonacci of 2, is the same as this one over here. All right? So for something as small as computing the value of Fibonacci 4, I have a lot of repetitions on the computation. It is true that some of them in this particular case are the base case or the initial condition, so I will kind of solve it quickly. But in any case, we can see that this is going to be very bad if, for instance, let's suppose that I wanted to compute now the value of Fibonacci of 5. Let's see what is going to happen. Basically, if I wanted to compute the Fibonacci of 5, I'm sorry, let me change that color, otherwise we won't see anything. There we go. Fibonacci of 5 going to be and then we can see that on going to be something like this. You see? And then we will have a now a big box here that is going to be there. All right. So the thing is, by doing something like this, we will get a solution that is very costly. If I don't remember bad, a solution like this is going to be of the order of it's exponential, the order 2 to the power of the n. All right. So it's bad. Now the thing is, how can I then improve the solution? By using dynamic programming. And what is that going to do? Well, what is going to happen is the following. Let's suppose, let me go back to my example, just to show something. Regardless of the order in which I will be computing, or the computer is going to be getting the numbers, the thing is, what if somehow when I compute this value, the Fibonacci of 3, whatever that value is, I store that, let's suppose, on an array. And then if I do so, let's suppose that I have this 3 of the computation of the Fibonacci. And then when I get the value of Fibonacci 1, I write it here. Well, in this case, since I am starting in 0, okay, I will put the value here. So this is going to be 1. This is going to be 0. And because I computed those two values here, and when I did, I wrote the solution on the table. So the next time I need the Fibonacci of 1, I can look at my table. This is going to be an array in position 1, and I can see that I already have the value, so I just take it from there, right? And then I can compute the value of 2. The value of 2 is going to be the addition of 1 and 0, which is 1. So I will put it here. And then when I go here to compute the Fibonacci of 3, I will add the 1 here, the 1 there, and this is going to be a 2. And then I move to this other position. The Fibonacci of 2, if I were doing like the normal recursion, I will have to decompose and call Fibonacci twice in order to get the solution. However, the first thing I will do is, instead of decomposing, I will check if in position 2 of my table, I already have a value. And that is the case. Here, I have a 1. So I don't have to do anything else but just to return number 1. All right. And then by doing so, I can add the 2 and the 1. So I will get the 3 over here. And then I will write that number in my table. So then I go to the right side of my tree. I will need to compute the Fibonacci of 3. But instead of doing all this decomposition, I will check in my table if I have a value different from 0 or from null, empty, in position 3 of my array, and that is the case. I have a 2. So I will just return the 2, and then I will add 3 plus 2, and I will have 5 here, and then I will write it 5 here. So you may have noticed that by doing this, every time I need a value that was already computed, instead of computing it again, I will get it from my table. So I have to pay the cost, the memory cost of having this array, which is going to be of size n, no bigger than that. But the process, the complete process, is going to be more efficient. And there is also another thing that you may have noticed. When we were solving the problem using my original formula here, I was filling up the array from left to right. So the solution that we are implementing or we are trying to define can also be considered as a bottom-up solution, which is the same, at least in this case, as having created an array with n numbers. Let's suppose that I am still talking about the Fibonacci of 5, and then start with the initial conditions, and from that I can continue filling up the array. Okay, so I just add these 2, I will get the 1, I add these 2, and then I will get the 2, I add these 2, I will get the 3. Oh, I'm sorry. There we go. These 2, and then I will get the 5, and so on. So we have now 2 possible ways of doing it. One, which is filling up the table by just adding the numbers from left to right, or implementing a solution using the recursion, but storing the information. So pseudocode for the first option would be something maybe like the following. Let's suppose that I have a function Fibonacci that is going to receive n, and this function is going to do the following. The first thing is that it will check. I will pass another thing as an argument to the function, which is going to be my array. I will call it solutions, but you can use any name. And then the first thing I will do is to check if solutions is not empty, then I will return the value in solutions n. That means that my array already had a value stored in such position, and if that is the case, I don't need to compute anything. I just need to return the value. But if the cell, that particular cell n, is still empty, it means that I haven't computed that value before. So I will need to do it. I will need to compute it. So in that case, I will do like the traditional function, recursive function, to compute the Fibonacci number. So in this case, what I will do is to check conditions. If n equals 1 or n equals 0, then I will say that the result is going to be 1. Oh, I'm sorry. In this case, it depends. If I am using the definition of the initial condition 0 and 1, then this is different. I was thinking in the other solution. Here is a 1. Now, let's see. This is 2. If it is 1 or it is 2, then I will return the value of 1. If I were using the other definition with the n equals 0, n Fibonacci of 0 and Fibonacci of 1 as initial conditions, I will have to change this a little bit. Then it would be 2 conditions. If n equals 0, then result is 0. If n equals 1, result is going to be 1. Okay, but this is easier because I have only one condition and the same answer. So this is just to check if this is the base case. Okay. But if it is not the base case, then I will have to do else Fibonacci of, I will have to compute that the result is going to be -2 plus Fibonacci of n minus 1. And then I will also, once I get the result, I will have to update my table. And that's it. Return result. And you can see that this line here is storing new solutions. So the cost of this version of my algorithm is going to be more cheaper than the other one, because I will have a number of operations here, this one, this one, this one, and this one. All of them are constant time. So that is O1. Here I will have, see, I will have to repeat this process n times here. N times. So my algorithm is going to be O of n. Okay, so this is way better than the other case in which we had, I'm sorry, in which we had the double exponential problem, right? Okay, so what other types of problems we may solve by using dynamic programming? Well, there are a lot of problems that can be solved this way. For instance, computing the binomial coefficient, computing the longest common subsequence in a string, implementing the Warshaw's algorithm for transitive closure in graphs, the Floyd's algorithm for all pairs shortest paths, also constructing an optimal binary search tree, and some instances of complex discrete optimization problems, such as the traveling salesman problem and the knapsack problem, that we will see both. Well, we will see several of these actually later on the class. But with this, we have a, I hope, general idea of how we can start looking at the problems like traditionally we did when using recursion, but now once we discover that the problem has this overlap when we do the decomposition, then we can apply this idea of having an auxiliary table where we can store the solutions we are getting in order to reuse them later on. And I will give you some other examples in separate videos so you can manage them more easily. For now, that's it. I hope this was an interesting topic for you, and see you soon.